Thank you. It is both an honor and a pleasure to give this presentation of the work of this year's Abel Prize winner. As well as that, it's an extremely daunting task. 2 years ago, I presented the work of John Milner, and I was able to put some nice pictures up so that even if people didn't understand what I was saying, they could look at the pictures. Last year, Endre Semeredi has proved a number of results that had rather simple statements, although the proofs were extremely hard, but at least I could explain the statements. This year, pretty pictures don't really help, and the statements themselves are not simple at all. So what do? Well, I'm going to have to restrict what I try to do. So instead of, I can't tell you about perverse sheaves and mixed Hodge structures today. I'm just going to concentrate on the Weil conjectures that we heard about, the first result that was mentioned in the citation, and try to give some idea of what that was. And in fact, I'll go back a stage further than that. I want to talk about the Ramanujan conjecture that was also mentioned. And that starts with something called Ramanujan's Tor function. So on the left-hand side of this equation, what do we see? We see Q multiplied by this pi symbol here stands for product. So it's a product as n goes from 1 to infinity of a whole lot of brackets, each of the form 1 minus q to the n to the 24. So this is shorthand for 1 minus q to the 24 times 1 minus q squared to the 24 times 1 minus q cubed to the 24 times 1 minus q to the 4 to the 24, and so on. So at school you may have seen products of brackets. The only difference here is that we've got infinitely many brackets and not just finitely many brackets. Nevertheless, it is possible to work out this product and write something on the other side that is a bit like a polynomial, except that instead of just finitely many powers of q, it has infinitely many powers of q with some coefficients. And the coefficient of q to the m is called Tor of m, and this Tor is Ramanujan's Tor function. So let's look at this in a little bit more detail and try and work out the value of the Tor function for a few small values of m. So what is Tor of 1? Well, what we want to do is end up with a q on the right-hand side by picking appropriate terms from each bracket. Now, the only way we can do that is to choose the initial q and then 1 from every bracket, because if we ever choose a power of q from any of the other brackets, it will multiply by this q and give a power of q that's bigger than q to the 1. So there's only one way of doing it, and that's why Tor of 1 equals 1. What about Tor of 2? Well, now we want to get 2 lots of q, and the only way we can do that is to choose the initial q here, which we're always forced to choose, and then one of these 24 q's, or rather minus q's, from the next 24 brackets. And we can't choose a q squared or q cubed, or we'll get a power that's too big. So we have 24 choices, each of which gives us a minus 1, so we get the Tor of 2 is minus 24. I'll do one more. So if we want to work out Tor of 3, our choices are, we have to choose this q again. We can either choose 2 q's from these 24 brackets, or we can choose 1 q squared from these 24 brackets. The number of ways of choosing 2 q's works out to be 276. That's 24 choose 2, if you know about that sort of thing. And since we're choosing 2 minus signs, that gives us a plus 276. And then we've also got the 24 ways of choosing a minus q squared, so we have to subtract 24 from that 276, and we get 252. And one can do similar calculations and so on. Now we could then ask, roughly how do these coefficients Tor of m grow as m goes to infinity? And Ramanujan conjectured that the size of Tor of m is at most the number of divisors of m, the number of numbers that go into m exactly, times m to the 11 over 2. In particular, if m is a prime, so if we call it p now, primes p have 2 divisors, and so it says that the size of the coefficient, the absolute value of the coefficient, is at most twice p to the 11 over 2. So I've told you officially what the conjecture is, but at this stage I would expect the typical reaction to be, well, that's a very strange thing to conjecture. Why do we define this function in the first place, and where on earth does this number 11 over 2 come from? So that's what I'd like to try to explain next. My explanation will necessarily be a partial one, but I can give some idea. So why is this bizarre-looking conjecture actually very natural and interesting? Well, one reason is that Q, I haven't told you this yet, but Q is actually standing for e to the 2 pi I z. So the function that we had, this big product, can actually be thought of as a function of z, a complex number. When we have a complex number, we can split it up into its real and imaginary parts. We write it as a plus I times b, where a and b are real numbers. And then if you work it out, the size of Q turns out to be e to the minus b, which is less than 1 whenever b is greater than 0. Because of all that, we can think of this as a function of z, and it turns out that that function makes sense whenever the size of Q is less than 1, and that's the case whenever the imaginary part of z is greater than 0. The complex numbers are typically represented on a plane. What this is saying is that we have a function, delta of z, that's defined in the top half of that plane, the part that's above the real axis. Now, so far that still doesn't really tell you why it's interesting, but the point is that this function delta turns out to have various properties that are interesting. So one of them is that, this is a simple one, delta of z plus 1 is the same as delta of z. That follows because e to the 2 pi I of z is the same as e to the 2 pi I z plus 1, because e to the 2 pi I equals 1. And so just when you change z to z plus 1, q doesn't change, and therefore the big expression in terms of q also doesn't change. So delta is periodic with period 1, in the sense that you can sort of shift the graph and it won't change. A much more interesting property, and this one I can't hope to justify, but I can just tell you it's the case. It turns out that delta of minus 1 over z is z to the 12 times delta of z. You should think of this as a sort of symmetry. If you replace z by minus 1 over z, and then you replace minus 1 over z by minus 1 over minus 1 over z, you get back to z again. So this is a way of saying that if you do this symmetry, which takes the upper half plane to itself, the function delta transforms in a very simple way. And it also has some more basic properties. It's called a holomorphic function. And holomorphic functions are very special functions that are rather sort of rigid. If you know the value of a holomorphic function in one place or in a little region, it tells you the value of that function everywhere. And because of that rigidity, it's rather difficult to combine the property of being holomorphic with these sorts of symmetry properties. So when you do manage to combine those properties, you get something that you like very much, something very special, and it's called a modular form. And modular forms turn up in many, many places in number theory, including, for example, Andrew Weil's proof of Fermat's last theorem, but that's just one of many examples. So modular forms are very interesting and important for number theorists, and they turn up. So that's one reason that the conjecture is interesting. Another reason is to do with writing numbers as sums of 24 squares. Supposing you've got a positive integer m, you'd like to work out how many ways you can write it as x1 squared plus x2 squared up to x24 squared, where all the xi's are integers. It turns out that calculating that exactly is not very feasible, but there is a nice approximate formula in terms of various other functions of a nice number theoretic kind. And Ramanujan's function Tor turns out to be the error term. So whenever you have an approximate formula for something, then the difference between the true answer and your approximate formula is called the error term. And the error term turns out to be this rather surprisingly interesting function, Ramanujan's Tor function. So once you've got an error term, you're interested in how small it is because you want to know how accurate the original formula was. So that gives a reason for wanting to know that Tor of m is not too big. You might ask, well, why are sums of 24 squares more interesting than sums of 17 squares or 96 squares or something like that? There are a couple of reasons for that, which I can't go into in detail. One is that this nice function delta of z that I mentioned before comes up when the number is 24, and it doesn't come up when it's, say, 17, or nothing comparable seems to come up. And another reason is that the number 24-dimensional space contains something called the Leech lattice, which is an incredibly symmetrical array of points. that you don't get in other dimensions. And because of that, there is something special about the number 24. I can't tell you, I have read on the internet that there is a connection between that and the importance of the Ramanujan function. But I confess that I don't know exactly what that connection is, but it exists. So we all have to take that on trust. Now, what about this number 11 over 2? Let's just think about that a little bit. I'm going to write S24 of m to be the number of 24 tuples that, when you take the sum of their squares, it adds up to not m, but less than or equal to m. Now, we can think of that in a very geometrical way. It's the number of integer points, so points with integer coordinates, that lie inside a 24-dimensional ball of radius the square root of m, because then this thing here is just by Pythagoras' theorem, this thing here is an expression for the square of the distance from the point x1 up to x24 from the origin. So this is saying that the square of the distance from the origin is at most m. In other words, the distance is at most the square root of m. So we're talking about the number of integer points in a ball of radius the square root of m. So how many integer points would we expect there to be? Well, we can give some sort of answer. The integer points are arranged in a nice sort of cubic lattice, and they have density 1 in space. So if you take a little sort of cube of volume 1, it'll contain one of those points. And the volume of the ball scales up like a power of 24, but as m scales up, of course, the radius is the square root of m, so the volume of the ball as a function of m scales like m to the 12. So as m goes up, the volume of the ball of radius root m goes up like m to the 12. So we would sort of imagine, if things look nice, that the number of integer points should be proportional to m to the 12. Now, what are we actually interested in? We're interested in the number of ways of writing x squared plus x1 squared plus x2 squared up to x24 squared equals m. But that's the number of integer points, that's the number of ways of getting exactly m. Sorry, that's the number of ways of getting at most m minus the number of ways of getting at most m minus 1. So it's S24 of m minus S24 of m minus 1. And so if S24 of m is proportional to m to the 12, then when you subtract the m minus 1 term, you'll get something that's proportional to m to the 11. So 11 has come in, which is promising. What about 11 over 2? Well, now we make a sort of leap of faith. Which is that we imagine a sort of situation a bit like this. Integer points that are near the ball sort of randomly decide whether to go into the ball or not. They sort of toss a coin and say, am I going to go in? And they decide like that. Because it's very difficult to predict exactly which points will be in and which will not. And it sort of looks somewhat random. Now, in random situations, if it were really random, then the standard deviation would be roughly the square root of the number of points we're talking about. And since we're talking about m to the 11 points, the square root of that is m to the 11 over 2. So in the best of all possible worlds, if things really behaved sort of in a random-like way, we would get this error term of m to the 11 over 2. And that doesn't tell you more, the more precise version of the Ramanujan conjecture, but at least it explains in some sort of heuristic way that why 11 over 2 is a natural sort of number to think about in this context. Now, you heard it described as the Riemann hypothesis for varieties over a finite field, the result that Deligne, one of the results that he is famous for. So let me just talk a little about the Riemann hypothesis itself, the normal Riemann hypothesis. So first we have the prime number theorem that says that the number of prime numbers up to n, this is another thing that you can't give an exact formula for, but you can give a very good approximate formula. And it's roughly what you would expect if each number just randomly decided whether to be a prime or not, and the probability that a given number m is prime is 1 over the logarithm of m. And so we get 1 over log 2 plus 1 over log 3 plus 1 over log 4 all the way up to 1 over log n. That's roughly how many primes you'd expect to get, it turns out. But again, we're interested in how good the approximation is. The prime number theorem says that's a fairly good approximation, but how good an approximation is it? Well, if you know the Riemann hypothesis, again, this square root error comes up. The error between what the prime number theorem says and the exact number of primes up to n should be not much more than the square root of n. I've been a little imprecise about the way I've stated that, but That's one way of formulating the Riemann hypothesis. I'll come to the more famous way of formulating it in just a moment. So now I'm going to change topic a little bit and talk about algebraic geometry over finite fields. So, as we heard, there's an important connection between algebra and geometry in that many shapes can be defined algebraically. For example, a circle, a unit circle in the plane is the set of points x, y, such that x squared plus y squared equals 1, and that's a nice polynomial equation. What's nice about these polynomial equations is that they make sense in other contexts that look a little less geometrical. So one of these contexts is called mod p arithmetic. So I'm taking p as a prime, and just for fun I'm taking it to be 13. So for arithmetic mod 13, the numbers go 0, 1, 2, 3, all the way up to 12. And when you get to 12, you go back to 0 again. And so you can imagine them going round in a circle. So if you want to do arithmetic, then 6 plus 9, well, you can imagine them as a clock face. If it's 6 o'clock and there are 13 hours on your clock face, then 9 hours later it will be 2 o'clock, because 6 plus 9 is 15, take away 13 and you're down to 2. And similarly, 4 times 4 is 3, because in the real world it's 16, then you take away 13 and you get the 3. And so we can define a unit circle, but this time thinking of x and y as being numbers mod 13. So an example of a point on the circle is the point 2, 6, because 2 squared plus 6 squared, that's 4 plus 36, is 40, and 13 goes exactly into 39, so 40 leaves a remainder of 1 when you divide by 13. So we get this rather strange kind of just collection of points dotted around. It doesn't really look like a real circle. It looks just like a finite collection of points. But we can sort of think of it as a kind of circle. And so one thing I now need you to know is that numbers mod 13 form a very nice algebraic system where you can add, multiply, and slightly more surprisingly, you can divide one number by another. And it turns out that there's something called a finite field whenever you have of size m, whenever m is a power of a prime number. Actually, I've called it p to the m. So for every p to the m, every prime power, you can find a nice algebraic system of size p to the m in which you can make sense of shapes like circles, except calling them shapes is now slightly misleading. And those are called varieties. And one of the basic things you can do, if you've got a variety, so a variety is some shape that's determined by some polynomial equations that makes sense when your algebraic system has size p, p squared, p cubed, p to the fourth, and so on. You can ask, how many points have you got when your algebraic system has size p? How many points have you got when it's got size p squared? How many points have you got when it's got size p cubed? And so on. So let's give a name to the number of points. We'll call it am. Now we define something called a zeta function, which I can't possibly justify why this is the right thing to write down, but it is. People thought about it very hard. This turns out to be a very important quantity. So the am, just to repeat, is counting how many points there are on your variety when the field has size p to the m. And so we form a sort of power series using the ams as coefficients and dividing by m, and we take e to that power series, and that gives us our function, which we call the zeta function. And Andre Weil thought very hard about these zeta functions and came up with a series of conjectures. I'm just going to tell you about one of them, which is that it should be possible to write a formula for this zeta function that looks a little bit complicated, but the main facts we need to know is that on the top of this fraction we've got a whole bunch of polynomials, and on the bottom we've got another whole bunch of polynomials, and the roots of the polynomial pi out of all these, there's got p0, p1, p2, p3, all the way up to p2n. The roots of the polynomial pi have size p to the minus I over 2. There's more that I could say, but that's what I want to say for the time being. And this divided by 2 is actually connected with the idea of a square root error, but I'll come to that a little bit later. And what about this? That's called the Riemann hypothesis, what I just had on the previous slide. That's the Riemann hypothesis for varieties over a finite field. So what does it have to do with the normal Riemann hypothesis? Well, for that, we define a different zeta function, the Riemann zeta function, which here s is a complex number. We take 1 to the minus s plus 2 to the minus s plus 3 to the minus s plus 4 to the minus s and so on, and add all that up. That formula only actually makes sense when the real part of s is greater than 1, but there are ways of making the function itself make sense to the left of the line of points with real part equal to 1. It's called analytic extension. We don't have to worry too much about that, except to say that what I said before about the error term in the prime number theorem turns out to be equivalent to saying that all the interesting zeros of the Riemann zeta function have real part equal to a half. So again, this number half comes up, and that's not a coincidence. That's all I really want to say. So there is a connection there. And just as the Riemann hypothesis is equivalent to the statement that the error term in the prime number theorem is of a square root type, it turns out that the Riemann hypothesis for varieties over a finite field is equivalent or can be used to show that many error terms of things that you want to count and have approximate formulae for in number theory are of square root type. And errors of square root type, that's somehow the best type of error that we can hope for. So this result has a very, very large, or the conjecture has a very, very large number of applications, and it is a result because that is the famous result that Deligne proved. So let's just very quickly say what Deligne did. So Weil had the extraordinary idea that one could use topological methods to attack his conjectures. In fact, the conjectures themselves were inspired by the thought that there was ought to be some topological theory in the background. This is very surprising because these circles that live inside finite fields, or powers of finite fields, or these other varieties, they're just finite sets of points. Topology is about sort of the continuous world, one might have thought. So what can one say about it? How can one use topology to talk about a finite set of points? Well, one can, and this was a suitable topological theory was developed by Grothendieck called étale cohomology. All we need to know here is that the word cohomology is very much a topological word, so it's a big surprise to see it coming up in a number theoretic context. But Gromov wasn't able to prove the Riemann hypothesis. However, he did, or the analog of the Riemann hypothesis, but he did have a very promising idea for how it should be done. Unfortunately, no one has made Grothendieck's very promising idea work. So it was a big surprise. One of the big surprises about Deligne's work was that he actually used a completely different approach. Or when I say completely different, he certainly built on what Grothendieck did, but he didn't use the plan that Grothendieck had for proving the conjecture. And finally, I just say once more that although what I've just described is an amazing result, it's just a small fraction of what Deligne has contributed to mathematics. He is really one of the absolute all-time greats. And just to convince you of that a little bit more, I'd like to end with a couple of quotations from Nick Katz, who wrote an article about Deligne after he got his Fields Medal in 1978. So one part of the proof, he said, Deligne's proof of this is simply spectacular. No other word will do. And when he goes on to describe the various steps of the proof, he just keeps putting in exclamation marks because the steps that Deligne takes are just so surprising. And if they're very surprising to Nick Katz, that's a much stronger statement than that they're very surprising to me. Nick Katz is one of the absolute world experts in this sort of area. And he ends by saying, I hope that I have conveyed to you some sense not only of Deligne's accomplishments, but also of the combination of incredible technical power, brilliant clarity, and sheer mathematical daring, which so characterizes his work.